All right, welcome back. Dr. P here, and in this lecture we're going to continue looking at some more reactions of aromatic compounds and also look at synthesis. So one thing that I want to do is look at electrophilic aromatic substitution with multiple substituents. And then we'll look at reactions of aromatic side chains. And I should probably say that that's side chains of aromatic compounds, not the side chains themselves are aromatic. And then we'll take a look at synthesis using electrophilic aromatic substitution. There is one more type of reaction, but I think I'll save that for a final lecture video. All right, so you may be asking yourselves the question, what if we have multiple substituents on benzene? Which one is going to direct the electrophilic aromatic substitution? And the answer is the stronger activating group is going to direct the location of where our substitution will occur. So if we have a summary, let's say we have a summary of our strength of activating groups and deactivating groups, as well as what are ortho, para versus meta directors, we can go ahead and make some decisions based on what our substituents are. And for that, I actually want to refer you to the following, and I'm going to zoom out a little. I'm going to post a copy of this. This is from another text, and let's remove that. And there is something similar in McMurray, table 16.2, so you can look at that. But this is from the Klein text, and I kind of like it because it sort of has everything on it, and it kind of captures where everything stands. So we have our activators, which are these up here, so above this line. And these include strong activators, so things like phenol, aniline, substituted aniline, and substituted anilines, phenoxide, very activated. Then we have moderate activators, things where we have a methoxy group, an amide or an ester attached via the amide nitrogen or the ester oxygen. That's very important. And then lastly, we have weak activators, which are just alkyl groups. And these, of course, are all ortho-para directors. Next, we have the deactivators, and the weak deactivators are when we have an alkyl, when we have a aryl halide, a phenyl halide. So we have a halogen here, chlorine, bromine, or iodine. It's a weak deactivator, but an ortho-para director. So that's, again, important to remember that. And then we have the moderate and strong deactivators, which are meta-directors. And these are things like carbonyls, whether it's a ketone, an aldehyde. We can have esters, carboxylic acids, amides, connected via the carbonyl, or I should say the carboxyl carbon. Okay, notice that's different than how they're connected up here. I may actually ask you to draw a mechanism for electrophilic aromatic substitution with one versus the other. We also have sulfonates and then nitriles. And then our strong deactivators are nitro, and then having multiple halogens on a carbon, and then positive nitrogen species. So if we have a quaternary ammonium salt, or if, say, we went ahead and protonated an amine, that would then be very strongly deactivated. And these moderate and strong deactivators are meta-directors. So I'll make sure that I post a copy of this in Canvas so you guys can take a look at that. All right, let's go back then and take a look, and I'll keep referring to this this handout figure here. Let's go back and take a look at some examples. Let me zoom back in so it's a little easier to see. Let's look at some examples. So let's say we had the following. I'll write these out here. Let's say we do Br2, Fe, Br3, and then let's do another one here. Let's do OH, CH3, and Br2, Br3. All right, so what are we going to get? Well, let's take a look. If we look at our table here, we see that, well, R is an alkyl group, and that's what our T-butyl is. So that is activating and ortho-para-directing. We'll just abbreviate ortho and para with O and P. And then our acetyl group here is this kind of species, and that's a deactivator and a meta-director. So in this case, our activating group, this guy, wins, if you will. So we're going to go ortho or para, so either there or there. You'll probably get a mix of products. However, you'll probably get more of one than the other. So ortho and para, and I would guess this guy would be probably the major product because the T-butyl group is fairly large. So substituting at the ortho position may be somewhat sterically hindered by the T-butyl group. If you drew either of these, that would be okay. If you're trying to use it in synthesis, you'd actually expect more of this product than you would of this product. Okay, let's look at the other one here. Now in this case, we have a strong activator. And it's an ortho-para director. And here we have a weak activator. Sorry. And it's, again, an ortho-para director. So in this case, this guy, the stronger activator, is going to win out. So that's going to determine where our where our substitution will occur. And it will occur at either ortho or para. Para already has a substituent on it, so it's going to be one of the ortho positions here. And we will thus get something like that. It could go to the other side, but that's the same thing, just flipped over. So there are some things to consider when we're thinking about where things are going to go for these ortho and para directors. We do want to think of the size of the existing substituent. And we also want to think of the size of the electrophile. And larger species, that is, larger substituents or electrophiles, are going to favor the para product. And that's simply for steric reasons. So what are some large and small electrophiles? I mean, you should be able to figure out large and small substituents. Highly branched alkyl substituents, like the T-butyl group, that's large. And OH is not very large. A halogen is not very large. So some large electrophiles would be SO3, so sulfonation. If we had CH3, 3CCl, so certain Friedel-Crafts alkylations. Again, we don't use the alkylation too much because we usually do an acylation. Small nucleophiles tend to be things like Br2. That's a smaller nucleophile. So let's see here. I think we'll talk about that a little bit later. Well, yeah, we'll talk about that a little later. See how we're doing on time. Okay. So these are just things to think about. And we'll revisit this when we talk about synthesis later on in this lecture. I do want to mention some other reactions, and that's specifically reactions of side chains of aromatic compounds. Now, we've already seen one such reaction, and it is a type of reduction. And so we saw ZnHg HCl aqueous. We saw the Clemenson reaction, and that will give us now our carbonyl fully reduced to an alkane. We could also do the following. Notice that this is an acid. If we didn't want to work in acid, we do have a reduction using hydrazine and KOH. This is called the Wolff-Kishner reaction. So let's say we had something where if we treated it with acid, another part of the molecule might react or something. Then we might want to use the Wolff-Kishner reduction instead. Now, McMurray does mention that you could use, so I'm going to say emphasize could, use H2/PD to reduce aromatic carbonyls. I tend to not want you guys to think about that, because then that leads a lot of students to think that, oh, I can do that for any carbonyl. No. We can't reduce all the way to an alkane with H2 and palladium or platinum or whatever. It only works for aromatics, and then only some aromatics. Now, there's one more reduction that I didn't mention. And that is, of course, something like NaBH4 in methanol or water. But, of course, that gives us now our alcohol. Now, carbonyls are not the only thing that could be reduced for the side chain on an aromatic compound. We could also have nitro groups can be reduced using zinc, or we could use tin or iron, and we will end up getting our NH2. And McMurray does mention that the NO2 group will also be reduced by catalytic hydrogenation. So that's one thing you have to watch out for. This Clemenson, these conditions are basically are really similar to the conditions for reducing the nitro group to an amine. So you have to be careful if you have a nitro group on your compound. You probably want to do the Wolff-Kishner instead, because that would reduce the carbonyl but not reduce the nitro. So it's always important to think about what other function groups might be present, what other substituents might be present, and if they will react with your reagent. All right. Now, those are just reductions. We do have oxidation. Where if we have our alkyl benzene here, if we treat this with KMnO4 in water and heat it up, we will get benzoic acid. It's such a good oxidizing agent that it basically blasts that apart. Note that this doesn't work, so I'm going to say but, it doesn't work for T-butyl benzene. Okay, so if we have a tertiary carbon there, we won't be able to oxidize that with permanganate. This is probably not as synthetically useful, but it's worth mentioning. What may also be synthetically useful is alpha halogenation. And so we could take our alkyl benzene here and treat it with NBS. To put a bromine on the alpha carbon. Okay, so this is our alpha carbon. Alpha carbon. If we wanted to stick a chlorine on, we can do that too. We could even use Br2 and HNu if we wanted to. We don't have to worry about the addition of Br2 to a double bond because, again, we've got our aromatic compound. It doesn't react to electrophilic addition. It does substitution. We don't have the conditions for substitution. Now, the mechanism for this is actually similar to what goes on with an allylic species. So I'll just mention here, alpha carbon, similar to allylic carbon. And so you can go ahead and draw resonance structures for the radical intermediate and see that the radical ends up getting delocalized on different carbons in the ring, and that helps stabilize the radical intermediate, which makes the reaction proceed. Okay, and again, that's sort of similar to the allylic carbon. Allylic carbon. There we go. Sorry about that. All right. Now, there's another set of reactions that I do want to go over, and it's actually something that's not done until chapter 24. So I'll mention it now, just so you've got these reactions, and you can read ahead in chapter 24 if you want. But it's the following reactions. Let me just jump right in here. So we'll look at reactions of aryl diazonium salts. And this is chapter 24. So we can take aniline, or really any amino benzene derivative, sorry about that, NH2. And if we treat this with NaNO2 and HCl, so sodium nitrite and hydrochloric acid, basically this is a stand-in for nitrous acid, so HNO2 is what we're making. We will get the following species. And then we'll have Cl- as the counter ion. And this is an aryl diazonium, aryl diazonium salt. Now, once we have this aryl diazonium salt, we can do a bunch of different things with it. We can actually swap out this, because look at it. That's going to be nitrogen if it leaves, right? If that leaves somehow, it's going to be nitrogen. So we could do a substitution reaction where, let's use CuCl, and we will get chlorobenzene. We could do CuBr. Get bromobenzene. We could do CuI and get iodobenzene. So this is a way to make iodobenzene. This works because our N2 here ends up being a good leaving group. So we would actually get the I minus, sorry, not the I minus, but we would get I adding in, and then the N2 would be leaving and replacing that. we could also do HBF4 and get our fluorobenzene. A couple of more here, or a few more. Let's see here. Let's use CuCN, and we will get now cyanobenzene. And let's see, let's go down here and do H2O and heat that up, and now we'll get phenol. We could use another alcohol, so ROH, and heat that up, and that would give us OR, our alkoxybenzene. And lastly, I'll put it over here on the side because it's kind of a funky one. We will use hypophosphorus acid, H3PO2. And what that gives us now is benzene. I'll put in the hydrogen just to show you that we're swapping out a hydrogen for the nitrogen. And you may ask yourselves, why would we ever do that? And the reason is that this could be synthetically useful. This now becomes a way to use this NH2 as a strong activating orthopara-directing group. Add some more things on, and then treat this to make it into the diazonium salt, treat with hypophosphorus acid to remove then the N2, which came from the NH2, and we'd be left with the rest of our compound. Okay, so let me just introduce synthesis here, and I think, you know, actually I'm going to maybe, oh gosh, we're getting close to half an hour here. I think I'll do a separate video for synthesis, but let me go ahead and just mention some things about synthesis. So some things to think about in synthesis. You need to think about the order of reactions. Okay, you can't always, let's say, brominate first and then acetylate. You'll end up getting a different product. So let's just say, for example, if I did this and I did Br2, FeBr3, I would get Br, and then if I do Cl, double bond O, and AlCl3, I would get Br, because bromine is an orthopara director, right? But if instead I did the following, AlCl3, oops, sorry. So there's my electrophile, and there's my Lewis acid catalyst. I'll get that guy. Now if I try to brominate, I'm going to end up with the meta product, because the acetyl group here is meta-directing. So notice the difference between these products. And it's just because we did the reactions in a different order. So that's one thing you have to think about. You also need to think about the size of the reactions and, the size of the reactants. So think about the size of substituents and electrophiles. And then I would say the last thing to think about is think about how you might do, separate ortho and para. So I'm just going to say separating ortho from para, or separating para from ortho. So if you get a mixture, presumably these have different boiling points, and you could distill and separate by distillation. But I'll show you a method for perhaps making just one of the two. Like let's say you just wanted to make the ortho. We could go ahead and do that. All right, well, I will leave that for the next lecture video. And until then, please stay safe out there. Bye now.